signal flow graph and Mason's gain formula. If we have a block diagram, something like this, then we can convert this block diagram into a signal flow graph. So to make the signal flow graph of this block diagram, we must take nodes for the mixers and takeoff points. In this block diagram, we have one mixer and one takeoff point. So one node for mixer and another node for the takeoff point. Apart from these two nodes, we'll take two additional nodes as input and output nodes. Now all the blocks are replaced by signals with respective gains showing the direction of flow of signals. So between mixer and takeoff point, the block G is connected. So between node 1 and 2, there is a signal flowing from 1 to 2 with gain G, and direction of signal is from 1 to 2. Similarly, there is another block connected between takeoff point and mixer, and it is going to minus of this mixer. So direction of signal is from node 2 to node 1, and the gain is minus H, because this H is going into the minus of mixer. That's why its gain is minus H. And nothing is connected between input node and the first node, so gain is 1 here. And nothing is connected between this takeoff point and the output, so gain is 1 here also. Now we will assign the node variables. For example, variable for node 1 is x1 and variable for node 2 is x2. So this is basically a signal flow graph for this block diagram. Now to find out the, yes, one more thing is there. For input node, variable is R, and for output node, for this output node, variable is C. Now we will write the node equations. We can write the node equations for all the nodes except for the input node. Okay, why? Because while writing the node equation, we only consider the incoming branches, and input node does not have any incoming branch. That's why we don't write the node equation for input node. So let's start with the output node equation C. While writing the node equation, we only consider the incoming branches. For at this node, one branch is coming from x2 and the gain is 1. So node equation is 1 into x2. For the second node, its variable is x2. Its equation is C, incoming branch. Only one branch is incoming at this node, that is coming from x1 through gain G. So node equation is G x1. This is the second equation. Now node equation for node 1, its variable is x1. So x1 is one branch is coming from R with gain 1, so 1 R. Another branch is coming from x2 with gain minus H, so it is minus H x2. Okay, now if we modify the three equations, or if we simply eliminate x1 and x2 from the three equations, then we can get the closed loop transfer function, that is C by R, and it will be G upon 1 plus GH. So that's how we can get the closed loop transfer function with the help of node equations. Okay, let's see one more example of writing the node equations. It is slightly bigger signal flow graph. Gains are A, B and C, and these are the feedback paths with gain minus D, minus E, minus F. Okay, so variable for input node is X, variable for output node is Y, and the other variables for the nodes are, say, X1, X2, X3 and X4. So for output node equation is 1 into X4, and then for node X4, node with variable X4, equation is CX3, and then for X3 node equation is BX2 and minus D X4, and then for node with variable X2 node equation is AX1 minus EX3, and for node with variable X1 equation is 1X minus F X2. That's how we write the node equation, and from all these equations, by eliminating X1, X2, X3 and X4, we can find the closed loop transfer function, that is Y by X, in terms of A, B, C, D, E and F. But this process is very tedious. It will take time, and a lot more eliminations are required. So it's better to solve or find the closed loop transfer function with the help of Mason's gain formula instead of writing the node equations. So before coming to the Mason's gain formula, let us see few definitions. First one is forward path. So forward path is the path from input node to output node without repetition of any node in between. And the forward path gain. Forward path gain denoted by P or P1, P2, like this. Forward path gain is the product of all gains in the forward path. Okay. Next definition is loop. Loop is a path which starts and terminates at the same node without repetition of any node in between. And loop gain is product of all gains in any loop. Then we have non-touching loops. Two or more than two loops are non-touching if the loops do not have common nodes, or loops without common nodes are the non-touching loops. If two or more than two loops have common nodes, then they are touching loops. Okay. So now let's see a few examples in which we will find out the number of forward paths and loops and non-touching pair of loops. In the signal flow graph, we will find out the number of forward paths and the loops. So path from input node to output node is forward path without repetition of any node in between. So this one is one forward path, 1 by S, 1 by S and 1, and its gain is 1 by S, 1 1 by s 1. So 1 by s square. This is the first forward path gain. Second forward path is 1 by s 1, 2 and 1. So its gain is 2 by s. So in this transfer signal flow graph we have two forward paths. Now let's see the loops. I will write the loop gain. Loop is a path which starts and terminates at the same node without repetition of any node in between. This is the actual direction. Okay, so here loop 1 by s and minus 1. So loop gain is minus 1 by s. One more loop is there, that is 2 and minus 1. So loop gain is minus 2. Another loop is 1 by s and minus 2. Its gain is minus 2 by s. And fourth loop is 1, 2 and minus 2. So loop gain is 2 into minus 2 into 1. So minus 4. So in this signal flow graph we have two forward paths and three loops, L1 with gain L1, L2, L3 and L4. Now let's find out the non-touching pair of loops. So see, in loop 1 and loop 2, these two nodes are common, so they are touching loops. For L2 and L3, this loop is L2 and this one is L3. So these two nodes are common, so they are not non-touching loops. For L3, L4, this loop is L3. Sorry, 1 by s minus 2 is L3. And L4 1, 2 and minus 2. So these three nodes are common nodes. So L3, L4 are touching loops. It means in this signal flow graph there is no pair of non-touching loops. Now let's see the number of forward paths and loops in this signal flow graph. So we can see one forward path is 1 by s, 1 by s and then 1. So its gain is 1 by s square. And the next forward path is 1, 2 and 1. So gain is 2. So in this signal flow graph we have two forward paths. Now let's see the loops. First loop is 1 by s minus 1. So its gain is 1 by s minus 1. So gain is minus 1 by s. Second loop is 1 by s, 1 and minus 2. So its gain is minus 2 by s. Now one more loop is there, that is 1 minus 2 and then 2 and back to the starting point minus 1. So the gain of third loop is 1 minus 2, 2 minus 1. So gain is 4. So in this signal flow graph we have two forward paths and the three loops, and there is no pair of non-touching loops. Now for the next signal flow graph, let's find out the number of forward paths and the loops. So forward path is the path from input node to output node without repetition of any node in between. So this signal flow graph has just one forward path, 1 into 1. Its gain is 1 into 1, that is 1. Okay, and let's find out the loops. One loop is 1 by s minus 3. so gain is minus 3 by S. Second loop is 1 by S minus 1, so gain is minus 1 by S. Third loop is 1 by S minus 2, so gain is minus 2 by S. Now we can see the first loop, this one is L1, and the second loop L2. Nodes are not common here, so there is non-touching pair of loop, and that pair is L1 and L2. This loop is L3, so we can see that in L1, L3 this node is common, so they are touching. In L2 and L3 these two nodes are common, so they are also touching. Just L1 and L2 will make a pair of non-touching loop. In this signal flow graph, we have just one forward path with gain. This is the forward path 1, A, B, C, D and 1. So gain, forward path gain is A, B, C, D, and it is quite visible that the signal flow graph has 4 loops. L1 is minus AH, second loop with gain B minus G, so minus BG, third loop with gain C minus F, so minus CF, and the fourth loop with gain minus DE. Now this is L1, L2, L3 and L4. Now if we write the non-touching pair of loops, then L1, L3, these two loops are non-touching. L1, L4 are non-touching. Then L2, L4, this pair is also non-touching. So we have 3 pairs of 2 non-touching loops. Now let's see the Mason's gain formula. To find the closed loop transfer function, C by R is 1 by del summation of Pk del K, where K is changing from 1 to N, where N is the number of forward paths. This equation can be expanded as 1 by del P1 del 1 plus P2 del 2 up to Pn del n, where this Pk is the gain of kth forward path. Okay, and what is del? Del is 1 minus sum of gains of all individual loops plus sum of products of gains of all pairs of 2 non-touching loops minus sum of products of gains of all groups of 3 non-touching loops. And so on. And what about del K? So del K is modification of this del. If we find del K, then del K is 1 minus sum of gains of all individual loops. We'll add one more term here, not touching the kth forward path. plus sum of product of gains of all pairs of two non-touching loops not touching the kth forward path. Minus sum of product of gains of all groups of three non-touching loops not touching the kth forward path. And so on. So if we find del 1, then it will be 1 minus sum of gains of all individual loops not touching the first forward path plus sum of products of gains of all pairs of two non-touching loops not touching the second forward path minus sum of products of gains of all groups of three non-touching loops not touching the first forward path. For del 2, k becomes second forward path. For del 3, k becomes 3, so it will be third forward path, and so on. So let us use the Mason's gain formula to find the closed loop transfer function for the different signal flow graph. We will start with this signal flow graph. We have all the information about forward paths and the loops. So for this example, y by x will be 1 by del p1 del 1. So first of all, let's calculate del. This is 1 minus sum of gains of all individual loops. So gains are L1, L2, L3, L4, and all the gains have minus sign, so I'll take minus common. So this will be 1 plus AH plus BG plus CF plus DE, then plus sum of products of gains of all pairs of two non-touching loops L1, L3, L1, L4 and L2, L4 are the non-touching pairs. So sum of products of gains of these loops. So L1, L3 means AHCF. Minus minus will be cancelled out. Then L1, L4. So AHDE. Sorry, not GH. AHDE. AHDE. And L2, L4. L2, L4. BGDE. BGDE. So this is del. Now what about del 1? Del 1 is 1 minus sum of gains of all individual loops not touching the first forward path. Here we can see that all the four loops are touching the first forward path. So there is no individual loop which is not touching the first forward path. So this will be 0. If there is no individual loop which is not touching the first forward path, so there is no question of pair of non-touching loops which is not touching the first forward path. So we don't need to find any further. So del 1 will be just 1. Okay, so we have del 1 and P1 is already there, A, B, C, D. So we can write, I'm writing here, y by x closed loop transfer function for this signal flow graph as P1 into del 1 is 1. So in numerator we will have A, B, C, D and divided by del. So this is the del. We'll simply replace this del here. So this will be 1 plus AH plus BG plus CF plus DE plus AH CF plus AH DE and BG plus BG DE. So this will be the closed loop transfer function for this signal flow graph using the Mason's gain formula. Now let's find out the closed loop transfer function for these two signal flow graph. So for first, C by R is 1 by del. Here we have two forward paths, so P1 del 1 plus P2 del 2. Okay, so let's calculate del. 1 minus sum of gains of all individual loops. So minus minus and this one is plus. So 1 by s plus 2 by s minus 4. And then plus sum of products of gains of all pairs of two non-touching loops. So here all the loops are touching, so no need to calculate any further. So del will be 3 by s minus 3. So this is 3 minus 3s by s. So this is del. Now del 1. Del 1 is 1 minus sum of gains of all individual loops not touching the first forward path. This is the first forward path, and we can see all three loops are touching the first forward path. So this is 0, del 1 is 1. What about del 2? This is 1 minus sum of gains of all individual loops not touching the second forward path. So all three loops are touching the second forward path. So this is also 0. So del 2 is 1. So C by R is P1 del 1. P1 is 1 by S square, del 1 is 1, plus P2 is 2, del 2 is 1 divided by del. Del is 3 upon 3, 1 minus S by S. So this is 2 S square plus 1 S 3s into 1 minus s. So this is the closed loop transfer function for this signal flow graph. Now let's come to the next question. Here we have just one forward path, so C by R will be P1 del 1 divided by del. So let's find del first. So del is 1 minus sum of gains of all individual loops. So all loop gains are negative, so minus minus plus. This will be 3 by s plus 1 by s plus 2 by s. So effectively it is 6 by s. Then plus sum of gains of sum of product of gains of all pairs of two non-touching loops. L1 and L2 are non-touching. So the product of gains is 3 by s square. 3 by s square. So del is basically s square plus 6s plus 3 by s square. This is del for this signal flow graph. Now we'll calculate del 1. So 1 minus sum of gains of all individual loops not touching the first forward path. So this is the first forward path, and we can see only L1 is touching the first forward path, and L2 and L3 are not touching the first forward path. So we have to consider L2 and L3. So both have minus sign, so this will be okay, minus 1 by s minus 2 by s plus sum of products of gains of all pairs of two non-touching loops not touching the first forward path. See, L2 and L3 are the individual loops which is not touching the first forward path, but these two loops itself are touching to each other. So there is no pair of non-touching loops which is not touching the first forward path. So it is 0. So del 1 is 1 plus 3 by s, or s plus 3 by s. So C by R is P1, that is 1 into del 1. So s plus 3 by s divided by del. Del is okay, s square plus 6s plus 3 by s square. So this will be s plus 3 into s divided by s square plus 6s plus 3. So this is the closed loop transfer function for this signal flow graph using Mason's gain formula. Now let's see the next example. For this signal flow graph, this is R, here we have C, and C by R is 1 by del, and here we have two forward paths, so P1 del 1 plus P2 del 2. So let's find del first. So del is 1 minus sum of gains of all individual loops not touching the 1 minus sum of gains of all individual loops. All loop gains have minus sign, so minus minus plus. This is 6 and 3 by s, so 3 by s plus 6, and then sum of product of gains of all pairs of two non-touching loops. So no pair of two non-touching loops, so it is 0, and it is 7s plus 3 by s. This is del. Now let's calculate del 1. 1 minus sum of gains of all individual loops not touching the first forward path. This one is the first forward path, and we can see all 4 loops are touching the first forward path. So this one is 0, so del 1 is 1. What about del 2? 1 minus sum of gains of all individual loops not touching the second forward path. This is second forward path, and we can see all 4 loops are touching the second forward path. So 0. Del 2 is also 1. So C by R is P1. P1 is 1 by S square into del 1, that is 1, plus P2, 2 by S into del 2, del 2 is 1, divided by del. So del is 7S plus 3 by S. So we can write it as 2S plus 1 into S by 7s plus 3. So this is the closed loop transfer function for this signal flow graph. Now let's see one example in which we will make a signal flow graph of slightly bigger block diagram. See, if in exam if it is asked to find the closed loop transfer function of any block diagram, so we can simply first make the signal flow graph of that block diagram, and by using the Manson-Gaines formula we can find closed loop transfer function very quickly. For this block diagram, let's make the signal flow graph. So to draw the signal flow graph, all the mixers and takeoff points are replaced by nodes, and 2 additional nodes are taken as input and output nodes, and then we will replace the blocks with signals showing the direction of flow of signal with their respective gains. But before doing that, let's find out the takeoff point which is connected just after the mixer. So we can see this is the takeoff point which is connected after this mixer, and one more takeoff point here, it is also connected after the mixer. So in such situations we won't take two different nodes, okay, because this takeoff point is taken at the output of mixer. So instead of drawing like this, we can draw it like this also. Now still the signal flow graph is same, okay, and if takeoff point is taken before the mixer, then we cannot do like this. We have to be very careful that if takeoff point is connected just after the mixer, then only we will do this modification, okay. Now we will count the takeoff points and mixers. 1 mixer, 2 mixer, this is takeoff point, and one more mixer. So 4 nodes, 1, 2, 3, 4, 4 mixers and takeoff points, and then 2 additional nodes as input and output node. Between node 1 and 2, nothing is connected, so gain is 1. Between node 2 and node 3, G1 is connected, so this is gain G1. Between 3 and 4, G2 is connected, so gain is G2. Between 2 and 4, G3 is connected, so gain is G3. Now between 4 and 2, H2 is connected, and between 3 and 1, H1 is connected. So between 2 and 4, this is H2, in fact minus H2, because minus H2 is going to minus of this mixer, and between 3 and 1, H1 is connected, so minus H1. 3 and 1, minus H1. Now between input node and first node, nothing is connected, so this gain is 1, and between fourth node and output node, nothing is connected, so gain is 1. So that's how we draw the signal flow graph. Now by using the Mason's gain formula, we can find the closed loop transfer function.